Hey everyone, thanks for joining this webinar, an introduction to FRP piping. My name is Dave Chapman. I'm a professional engineer and the sales and service manager for RPS Composites. And this is about a 50-minute webinar, an introduction to FRP piping. There's going to be some other webinars on the website that you can check out that are a little shorter and more specific. But if you want to know a little bit more about generally about FRP piping, if you're in engineering, if you're in maintenance, or you're in procurement, I think it's a good introduction for you. So what we're going to talk about is briefly talk about RPS Composites, what RPS Composites is, who we are, and then what is FRP piping used for, and what is FRP piping, the glass, the resin, the corrosion resistance. FRP piping versus metallic piping, that's obviously a question that comes up a lot, why you would use FRP piping, how you design FRP piping and fittings, and the codes that apply, using FRP above ground and below ground, indoors and outdoors, how you join together FRP piping and how bonders are trained, the bonder qualification process, the quality control that goes into FRP piping, and specifically for piping, the supports that you use for FRP piping. It's a little bit different than the supports you would use for metallic piping. And finally, we're going to touch briefly on pipe stress analysis for FRP piping. And then at the end here, you see there's questions and answers. So this is a webinar that you're watching. You can please, at the end, there's going to be some contact information so you can follow up if you have any questions, and you can also go to the website. There's contact information on the website. And if you did want this as a live event, so if you wanted to have a lunch and learn, no problem, we can do that as well, and then you can answer questions on the fly. Just contact us. You'll see some contact information on the website about having your own live event. If you wanted to do that for a group of people, it's no problem. We do it all the time. So just briefly, who is RPS Composites? Well, like many companies, we've started out with some different names than RPS Composites, and we were actually started out in around the 1960s as ABCO or ABCO Plastics. And a lot of people are still familiar with that branding. It still appears in some specs, and that is our original company name. In around 1989, we changed to Reinforced Plastic Systems, and we procured some other FRP companies like Non-Metallic Resources and Shenandoah Fiberglass. And in the the 2000s, we changed to RPS Composites, and that's how we're known today as RPS or RPS Composites. And we have 8 manufacturing locations in the US and Canada. We actually only have 1 in Canada and 7 in the US. We've got about 300,000 square feet of manufacturing, about 300 employees, about 100 field service technicians, and I'll tell you a little bit about that after. We have 70 staff, which is engineers, technologists, project managers, supervisors, administrative support. And what we do at RPS is primarily FRP piping and dual laminate piping, and I'll tell you a little bit about dual laminate piping after. We supply pipe supports. We do some FRP duct and custom FRP, also some vacuum infusion of beams and covers, and troughs and baffles and weirs. So when it comes to RPS Composites, we've got a few brands that have been kicking around since the 1960s. In FRP, we have our P150, A150, H150. Those are what we call HPPE, so high performance pre-engineered, meaning that these are in stock actually, and they're already pre-engineered, so it's something that flows through the shop quickly. And we actually have some variants of these that are also pre-engineered but not in stock. And then we have totally custom pipe if you had a particularly custom FRP piping spec. And on the dual laminate side, the HPPE or the pre-engineered stuff that's in stock is generally the Maxar brand of dual laminate, which is FEP or PVDF. And we also have the PFA version of that as well. Then there's some other variants of dual laminates that I'll talk about after. And finally at RPS, the other thing we do, the other half of our equation is field service. So we make piping, well, of course, we also install that piping. We do linings, which is where the tanks come in. We'll inspect tanks, we'll line tanks, we'll do emergency response for tanks or pipes that are leaking and need maintenance. Inspection, like it says down there, we do a lot of inspection of tanks and maintenance. You know, most maintenance shops are not really experienced in doing inspection of tanks or pipe, and some are not really set up to do emergency repairs. So that's about half of our business. And on the engineering side, we really don't sell engineering services too much. We spend most of our time doing component design. We do some pipe stress analysis. Mostly, as I'll tell you later, we actually tell people how to do the pipe stress analysis on our pipe and maybe check out a few of their first iterations, and then they're off to the races. So where's FRP pipe used? Well, a big use since the 1970s has been in coal-fired power stations for something called flue gas desulfurization. There's a lot of FRP pipe used in recycle pipe. Here you can see some large diameter recycle pipe. Inside the FGD absorber towers, the FRP is commonly used in the spray headers. In the process side of things, when you have gypsum slurry, limestone slurry, dewatering pipe, FRP is commonly used. You can see a couple of instances of FRP pipe here next to some steel pipe actually. And most recently, FRP has been used a lot in CCR, ELG regulations, piping required for wastewater treatment at coal-fired power stations, and actually for other wastewater treatment applications. And the gray pipe in the picture is actually some CCR ELG pipe, and the other stuff is some wastewater treatment piping unrelated to coal-fired power stations. But FRP piping is used a lot in a variety of other applications. Mineral processing, you have electrowinning using lots of acids and caustics and other chemistries. It's very common to use FRP piping. Pulp and paper, where you have a lot of acids and bases. And just in general, chemical processing, chlor-alkali, sulfuric acid. You can see a whole list of end users there who would be using a lot of FRP piping. So what is FRP? Well, you've heard of FRP. You might have heard the word fiberglass, and with the French spelling, FRP or GRP if you're in Europe or South America. And what fiberglass is, well, you see it every day. Maybe not this one. You might see driving around, or you see some boats in the water. You see some tanks around, some piping at all kinds of different chem process sites or power stations. And more nowadays, you see grating and actually structural components that are all FRP. And FRP is actually a thermoset resin, and that's what gives you the chemical resistance and actually holds the fibers in place, and glass fibers that give you the strength and the stiffness you're looking for. And when it comes to resin, most people actually are familiar with thermoplastic resin. You think of PVC, HDPE, those are thermoplastic resins, and I think of them like an ice cube, because if you're making PVC pipe, what you would do is you would heat up the beads of PVC and you would extrude those through an extrusion process to make PVC pipe or HDPE pipe. And if there were defects in the end product, what you would do is grind it up, melt it back down, and put it back down through the process. So think of it as an ice cube that can be frozen and melted back again, and you keep getting the same thing over and over again. But a thermoset resin that's actually used in FRP is a little different. And you might think of it like a fried egg. Once I break the yolk, the egg, and put it in the frying pan, it comes together and it can't be undone. And that's like catalyzing a thermoset resin. It actually sets off a chain reaction, and there's cross-linking that takes place, and you have 15 minutes, 20 minutes, an hour, depending how you set up the resin. And once it solidifies, it stays as a solid and can't be turned back the other way. And when it comes to thermoset resins, there's actually 3 types of resins that are most popular. There's a couple others, but generally they come down to 3 types. And that's polyester resin, epoxy resin, and vinyl ester resin. Polyester resin is the most commonly used thermoset resin, probably by volume, because it's used a lot in boats and in municipal waste water treatment sewers where you have low corrosion requirements. It actually has good resistance to acids, but it has relatively low elongation, meaning it's relatively brittle, and it actually has poor secondary bonding characteristics, meaning it's a little tricky to bond one piece of polyester to another piece of polyester. It is less costly than epoxies and vinyl esters. That's why one reason why it's the most commonly used in municipal applications, for example. Epoxy you've heard a lot of. That's a little different than polyester because polyester, I catalyze it. With epoxies, I have a resin and a hardener. And epoxies have great strength. They're used a lot in aerospace or recreation, oil field piping. They have great bonding characteristics. That's why adhesives, if you go to the dollar store or Dollar General and you get a little 2 tubes of adhesive that come together, it's actually epoxy. It's an epoxy resin and it's an epoxy hardener. The corrosion resistance of epoxies are generally not comparable to the vinyl esters and polyesters and are very dependent on the hardener that's used. And the hardeners and epoxies are actually made by different companies. So it's a little bit more complicated to get the corrosion resistance of an epoxy. They're also much more difficult to work with. Epoxies are very sticky, unlike the polyesters and vinyl esters. And you're just generally going to mostly see them used in piping on the commodity side in oil field piping. Vinyl esters, which have actually been around for over 50 years, are the most commonly used resins in corrosion applications. What a vinyl ester is, it's actually called epoxy vinyl ester because it's a polyester resin that has an epoxy backbone. And what that does is the epoxy backbone gives the polyester resin the characteristics of an epoxy. So the secondary bonding characteristics and the elongation is better, closer to an epoxy. But the corrosion resistance is more like a polyester. So really you kind of get the best of both worlds, the workability, the corrosion resistance, the toughness. You get all those great characteristics of both the epoxies and the polyesters. And that's why these resins have been used since the 1970s. So they've been used for over 50 years. So when it comes to choosing a resin, well, how do you do that? Well, normally you or an engineering company or an end user is going to have a process stream. And what you do is you can actually look up the most basic process streams in the chemical resistance guide. We actually have our own chemical resistance guide, and you would look up that process stream and it would tell you whether the particular vinyl ester resin was acceptable, what concentration and what temperature it might be acceptable to. Often if the process stream is a little more complicated, what we do is we go to the resin manufacturer themselves. INEOS is the one we use, and we go to INEOS and we ask them what type of resin is going to work best in this process stream, or is there even an FRP resin that will be acceptable? And once you've got the resin, then you've got to figure out, do I have to add something to the resin? Typically, we add things called thixotropes to make the resin thicker. We sometimes add aluminum oxide or silicon carbide to make the resin abrasion resistant. We can add antimony agents combined with the resin manufacturer, adding bromine to make the resin have a lower flame spread. Of course, we can pigment the resin like you see in the picture. And then we're going to add different things to catalyze and promote and accelerate the resin. That's going to affect the gel time and the working time you have with the resin. On the glass side, we actually use glass to reinforce fiberglass because it's the most inexpensive, relatively speaking, of the reinforcements. When you talk about carbon fiber or Kevlar or armored reinforcements, glass is made from silica, which makes it much more inexpensive. And basically what the glass manufacturers like Owens Corning do is take silica, heat it up to a molten state, put it down through fine dyes, and then they apply a sizing agent to the glass. Actually, they use something called silane. And what that does is that sizing agent bonds to the glass and the resin bonds to the sizing agent, and that's how you get a bond between the glass and the resin. The glass actually comes out in a glass roving, like you can see on the left-hand side, but you can imagine that glass roving is going to be a little difficult to use to make a 1-inch flange, for example. So what the glass manufacturers do is chop up that roving, spray it down, and spray a binder to hold it in place. And what you get is something called chopped strand mat. That's what's shown in the middle of the picture. That chopped strand mat is great for corrosion resistance because the glass fiber is chopped up, and that makes it much more difficult for chemicals to get through the glass reinforcement to wick along the fiber. However, you only get about 25% reinforcement when you saturate it with resin. So another way to reinforce the fitting is to use a woven roving. So I've taken the glass roving and I've woven it into a matting, like you can see on the right hand side, and that sheet material, which is woven roving, can be used to reinforce larger fittings. So what we do to make a laminate, and this would apply to tanks or piping, is we first apply a resin-rich area to the process side, and we actually use something called a surfacing veil. So it's sort of like the chopped strand mat, but much thinner. And it comes in a polyester version or a glass version. There's certain times when you'd use one or the other. And what you get is about 90% resin. So we don't have 100% pure resin barrier that might be susceptible to thermal shock. We have about 10% reinforcement. So a little bit of reinforcement, but a lot of resin to give you corrosion resistance. And then behind that, we typically put a couple layers of that chopped strand mat, and that combined with the chemical veil gives you a lot of corrosion resistance and a lot of resin. So behind that, we need to have some strength. So what we do is we either use the glass filaments or a combination of the chopped strand mat and woven roving to get you a higher glass content in the structural layers, where you might have between 50 and 70% glass. So when you're making a product, and again, this would apply to tanks or piping, you take the glass and you saturate it with resin, and you have two ways of making something. Generally, one is called hand layup or contact molded, and this is the most basic way of making anything out of fiberglass. So what you do is you catalyze the resin, and you take your glass reinforcement, and in the middle of the screen, you can see the person has saturated that glass reinforcement with the catalyzed resin, and on the right hand side they're going to apply that to, in that case, a butt joint. Over on the far right you see the woven roving. That's actually a bit of a different process that is going to be saturated separately and applied to make a flange, but it's all done by hand, so you can see it's going to be pretty labor intensive. Here's a quick video that shows you how the hand layup or contact molded process actually works. So here's a technician making a tee. So what we've done here is the technician would have been told or described to say, hey, use this particular style of resin and this particular catalyst. It would be pre-mixed for them. The technician would catalyze the resin depending on the temperature, the size of the item they're working on. And then they're going to saturate the glass reinforcement, apply that saturated glass reinforcement to the mold. And what you're seeing now is the technician is rolling out all the air that's in the laminate. The laminate is going to be full of air when you apply it to the mold, whether it's a butt joint that you're doing in the field or making a fitting here in the shop. So the laminator, the technician, rolls out all that air, and here you can see them applying a second layer of reinforcement. It's actually the top piece of the tee in this case. They've saturated that second layer of reinforcement. They're just going to finish rolling out the air from the first layer. I think she actually cuts a little bit off here because the glass kit that was pre-kitted was a little long in this case. She rolls it out, and then she's going to take that other layer, which actually goes around the top of the tee, and repeats the process. So you can see it's pretty labor intensive. This is actually the same way when I show you a butt joint, how you join the piping. This is actually the same way you would do a butt joint in the field. And this is how the fittings are made by contact molding. So when it comes to making pipe, you can actually make pipe the same way. You could saturate by hand the glass and apply it to the mold. And what you're seeing on the left-hand side there is a person has taken the chop strand mat and they're actually applying the corrosion barrier by hand. So they've saturated the resin, they put some wet resin on the mold there, and they're going to spiral on some chop strand mat to put on the corrosion barrier in the piping. And you could continue to do that for the structural layers, but a quicker way to do that, a more efficient way, more cost-effective way, is to filament wind the pipe. So I take the glass rovings now, I run them down through a bath of resin, and I spiral them onto the piping. And you can see here in this picture, here's how it's done. So in this case, the operators have already applied the corrosion barrier to the pipe. In this case, the corrosion barrier actually has silicon carbide or aluminum oxide because it's used for an abrasion resistant application. Now they're applying some catalyzed resin over the cured liner to get a bond. They have a predetermined set of rovings, a pattern that runs down into the catalyzed bath of resin. So engineering would have given them the number of rovings to tie onto the carriage. And then they also have a predetermined program. In this case, it's a PLC program that controls the movement of the carriage relative to the mandrel. He dumps in some catalyzed resin. He's going to tie on the rovings onto the mold, and then he's going to set the program in motion, and you're going to see it's going to wind a 55-degree pattern, in this case actually, onto the mold, and that will spiral onto the mold. And what that does is it gives you about 70% glass going onto the mold and about 30% resin. And that allows us to make the pipe thinner, relatively speaking, compared to a hand layout pipe. I can get the same pressure rating with less thickness because I have a higher glass loading. You can see here how it spirals down. And actually, when that comes back, that band of reinforcement is going to lay right beside the first band. And that's how filament wound pipe is made. So why would you use FRP piping? Well, as you guessed, you're going to use it for corrosion resistance. If you look at this table here that compares vinyl ester FRP to 316, that should say L, I think, stainless steel piping, 2205 alloy, a C276, and rubber lined steel, and we're looking at sulfuric acid, hydrochloric acid, and chlorides, you can see the vinyl ester resin really outperforms them all when it comes to corrosion resistance. And actually the temperature resistance of the alloys is not much different than the vinyl esters. It's actually much lower for certain concentrations of chemistry. So basically the reason you're going to use FRP is corrosion resistance. You're going to be limited to about 212F. You can see there, that is kind of the limitation of FRP. So it's kind of definitely has its niche when it comes to corrosion resistance, but also has its limitations when it comes to temperature resistance. So how does FRP compare to metallic piping and other materials? Well, steel is ductile and it will deform before it breaks. FRP is not ductile. It'll break once it reaches its ultimate strength. However, it doesn't brittle at low temperatures like thermoplastics, PVC or HDPE. Steel is very stiff, has a modulus of 29 million. FRP is much less, around 1.5 million. And that means you need more pipe supports in a FRP system than you would in a steel system, but less than HDPE. The joints are much wider than steel, where you can just weld the two pieces together. In FRP, you either have to bond the pieces together or laminate the two pieces together. So typically the joints are about a diameter wide. FRP is lighter than steel, but heavier than HDPE. And usually that only comes into effect in actually handling the pieces of pipe. FRPs definitely handle. You can pick up a piece of 6-inch pipe. That would be practical for steel, for example. FRP pipe expands more than steel, but less than HDPE. So if you look here, FRP has a coefficient of thermal expansion of 25 compared to 12 for steel and 100 for HDPE. When it comes to standards, there's a lot of standards out there, but until recently, there actually hasn't been one good standard for FRP piping. There has been a standard kicking around since 1969 called PS 1569. It was intended for polyester resin and contact molding, so it wasn't made for filament winding. And the corrosion barrier is included in the wall thickness calculations in the spec, which is generally not recommended nowadays. And the properties used in the spec are very conservative. It's still widely referenced, although it's been out of print for decades. For actually making the filament wound pipe, or something called centrifugally cast pipe, where you spin the mold and you put the resin and glass in the spinning mold, there are two ASTM standards, 2996 and 2997. These are pretty widely used. They won't tell you exactly what the thicknesses are going to be. They'll tell you how to rate the piping. So when you come up with the thickness, tells you how you would rate the piping. There's a good standard, ASTM 6041, for contact molding. This is actually what we've used to design most of our fittings. It requires a design factor of 6:1, and then you do a proof test of 4 times the design pressure to actually proof test your components. And filament wound pipe is not covered under the standing. It's for contact molded, so the filament wound pipe would be covered under the 2996. But there is a great standard when it comes to tanks called RTP1. It's very comprehensive, and it covers full vacuum to 15 psi. So it doesn't apply for pressure vessels, but it does apply up to 15 psi. It's a really detailed standard, tells you all about design, qualification, testing. And in the US, there are currently 12 fabricators who are able to stamp a vessel to RTP1. You get above 15 psi, you need to go to the Boiler and Pressure Vessel Code, Section 10, which has, similar to RTP1, has a lot of design criteria in there. And currently there are 4 fabricators who can make a stamped pressure vessel. The two process pipe codes, ASME B31.3 and B31.1, they each have sections that address non-metallic piping. They won't tell you how to make the piping, how thick to make the piping, how thick to make the fittings. What they do is reference standards like the D2996, for example. There is a section, some rules for pipe stress analysis, although not a lot of information. And there is a section on bonder qualification, which I'll talk to you a little bit about later, but really B31.1 and B31.3 don't give you a lot of guidance when it comes to FRP piping. Fortunately, in 2019, there was a new standard released by ASME, NM2, and NM2, much like RTP1, is really the go-to for FRP piping. Eventually, it should be adopted into B31.1 and B31.3. At the time of this webinar, it was not, but the intention is B31.1 and B31.3 will simply go to NM2 for FRP piping. It has a section on bonder qualification. It applies up to 250 psi. And it has 4 design methods that you can use to qualify your pipe and fittings. So it's pretty detailed. And when someone says they're qualified to NM2, you know that they've used one of these 4 rules to come up with the justification for their pressure fitting design. So FRP pipe, it can be used above ground and below ground. Both are pretty common. Above ground FRP pipe, you have to look at the hanger spacing. It's going to be a little different than metallic piping. You can actually see in this slide that over here there are some kickers that have been added so that the FRP pipe could work within the span requirements that the manufacturer has laid out. This particular pipe rack was probably a little too long for the size of that particular FRP pipe. You're going to anchor the pipe generally once every straight run, and I'll show you later how you actually anchor the pipe with an FRP collar. At least every 4th support, you're going to have to guide to prevent sideways movement. Generally, you don't let FRP pipe snake along like you would with maybe HDPE pipe. So you just put a U-bolt or a U-strap over the pipe at least every fourth time, and sometimes in different areas where you have earthquake loads, you need to have more than that, or wind or seismic events. And you're doing a pipe stress analysis, you may need actually more than every fourth support to be guided. It can be insulated and heat traced, and we'll talk a little bit more about that and talk about pipe supports in a later section. So you can do both of those. You can insulate and heat trace the pipe because it can't be allowed to freeze, and the pipe supports are kind of special for FRP pipe, and I'll talk about more about that shortly. The valves for when you're laying out FRP pipe, heavy valves or equipment, they need to be supported separately or with a support close by. And you can see in the picture here, I've actually used a flange support to pick up those valves in the picture. And above ground FRP pipe, water hammer is a no-no in FRP pipe. You want to try to minimize that as much as possible. It's not as forgiving as it is in metallic piping, again, because it's not elastic like metallic piping is. You've got to allow for field joints and changes in direction. So you can't, if you had two flanges, you can't just draw the flange in place to make it fit. It's actually got to fit in place unstressed. You got to make sure your pipe supports are away from your joints. And again, you can assume that those joints are going to be about a diameter wide. And you got to keep the pipe supports also away from elbows, and you have to have this lateral free length. There's some guidelines in our design manual of how to do that. And very importantly, you got to use the right type of flange connections when you're dealing with above ground FRP pipe, and I'll tell you a little bit more about that later. To control thermal expansion, you can use changes in direction, you can use expansion joints, expansion loops, or you can actually rigidly design the piping system so you can anchor the system all over the place. Because of the relatively low modulus of elasticity, you can actually do that in FRP pipe quite nicely. When it comes to the actual dimensions of FRP pipe, FRP is generally speaking all based on the ID. You saw the person laying up the T. Well, they start out with a T mold that's 3.0, and they apply reinforcement, and the finished is 3.41 or some strange number. So everything has a fixed ID, and then the OD is going to vary by the component, the liner thickness, the pressure rating, all that sort of thing. Dimensions of the actual fittings will vary a bit by manufacturer. They're generally industry standard dimensions, but like I say, they will vary a little bit depending on especially how you're joining the fittings together. You can have steel fitting dimensions, so you could have an elbow like this that's a relatively short flange by flange elbow, but they're generally going to be expensive in FRP, because now if you look at this fitting, this elbow, I'm going to have to laminate a flange on each end of the elbow directly, and that's going to be expensive. I can't slip it on and weld it on like I can in metallic fittings. What I'd prefer to do is something like this, where I have a female bell end and I use a nipple and I bond on a flange as a secondary process. If you're modeling FRP piping, there aren't a lot of good options for you to model FRP piping. We often see people use metallic piping, and that gets them into a bit of trouble when they do a 3D modeling. We fortunately have an FRP content pack for AutoCAD Plan 3D, and we actually are in the works for Hexagon and Aviva E3D. So look for those and just go to the website and you can get a link to download all that stuff. When you use FRP piping indoors, not really any special requirements. Of course, if the pipe is carrying some dangerous chemicals, you'd need to protect it from vehicle traffic or other sources of damage. If it's in a corrosive area, one of the beauties of FRP piping is, the exterior corrosion resin that's on the pipe is pretty corrosion resistant compared to metallic pipe. It's not quite the same as the inside surface where you have a much thicker corrosion barrier, but that layer of resin and glass that's on the outside of the pipe is pretty corrosion resistant and gives you really good corrosion resistance in most environments. If you had a really nasty environment that the pipe was exposed to, or the pipe's actually down inside of a tank, you would need to apply a corrosion barrier to the outside of the pipe. One of the nice things too about insulating FRP pipe is you don't have to worry about moisture getting in between the insulation and the piping. It's not going to attack the FRP from the outside like it would in metallic piping. And of course, indoors, like you can see in the picture, you can pigment the pipe any style you want. You could put stripes on it and do pretty much whatever you'd like to do as far as coloring goes. When you get to outdoors, FRP pipe is used a lot outdoors as well. The pipe will be finished with a UV inhibitor, and that's really important. You can see in the picture at the bottom, actually that's an old piece of pipe from up in the boneyard, and on the left-hand side, the pipe has the UV inhibitor in it, and on the right-hand side was just a cutoff from the mold. And you can see it looks like that chop strand mat, and that's actually something called fiber bloom, where the resin has been taken away from the UV in the wind and the glass fibers are exposed. So that will happen if you don't use a UV inhibitor. If you use a UV inhibitor, you won't get that phenomena for many decades. And it's really just a cosmetic phenomenon anyway. You could coat over top of that with an epoxy resin or something. But like I say, you're not going to see that for decades if you use a UV inhibitor. Also, pigmenting the pipe will help with the UV degradation. The pipe can be insulated and heat traced. I mentioned that. Just keep the temperature of the heat tracing less than the rating of the pipe, so usually less than 180 degrees F. You have to think about snow loads and wind loads, and I'll talk about that when we talk about pipe stress analysis. Well, let me talk for a minute about something called dual laminate pipe, because that's a bit different than standard FRP pipe. So sometimes when you get a severe service like sulfuric acid, concentrated sulfuric acid. If you go look in the corrosion guide that we have, you're going to find that straight FRP pipe is not recommended for concentrated sulfuric acid. However, what you can do is line the pipe with, for example, Teflon. So in this case, you've actually got two examples here. We've got the pipe on the left-hand side is lined with FEP, and in the middle, it's lined with Kynar. And I say lined, but it's actually a little bit different than lined steel, because what we do is we take tubing, Kynar tubing or FEP tubing, we embed glass onto the tubing, and then we lay up over top of it. So you get a bonded liner to the pipe. So the liner and the FRP are all in one. So you have the properties of an FRP pipe. So you think about when we use HDPE, for example, you have the properties of FRP pipe, not HDPE pipe, but you have the chemical resistance that you need. So for example, the chemical resistance of Kynar, and that's why you can use sulfuric acid. The Kynar will resist that, or the FEP, but you have the corrosion resistance and the strength and lightweight characteristics of the FRP. Yeah, and this just says in the next slide that the corrosion barrier is the thermoplastic, and the rest of the pipe is just the same FRP pipe as your straight FRP pipe that we've been talking about all along. Here's a quick overlay of the types of dual laminate pipe you can make. The premiums are going to be the fluoropolymers. They're what we call our HPPE, so our high performance pre-engineered pipe. Those are the ones that are in stock and most commonly used because they cover the widest array of service conditions. Sometimes you can get it in a polypropylene or the CPVCs, PVCs. Those are used in chlorine services. They're a little less expensive than the fluoropolymers. But like I say, overwhelmingly, we probably supply FEP and PVDF for dual laminate systems. When it comes to joining FRP, really the thing that the takeaway here is that both the shop and the field joints need to be made by a qualified bonder. Okay, just like if you're doing metallic pipe and someone has a welding ticket or is a qualified pipe fitter, it's the same in FRP. You have to be qualified to do the joints. What we usually like to see is to have about 2/3 of the joints done in the shop and maybe leave about 1/3 of the joints done in the field. That will reduce the cost because we can do the joints in the shop quicker and cheaper than you can do them in the field. It'll condense the schedule because we can do them faster, and it'll reduce the risk because the men and women are doing these pipe joints every day in the shop. Having said that, we can train people, and you could do 100% of the joints in the field if you wanted to, or we could do 100% of the joints in the shop and just send out completely flange system. That's not out of the question. You can see over in the right hand side though, we usually try to eliminate as many flanges as we can. The flanges in the picture in the middle and over on the right, they're just used for connections to equipment. That's the way we prefer to do it. So that the elbow, for example, at the end of the first picture is not a flange by flange elbow. Those are shop joints in the fittings. And when it comes to joining methods, there are actually 4 types of methods we use. So we use something called button wrap joints. Those are by far the most common type of joint, where we actually laminate the 2 pieces of pipe or the pipe and fitting together. There's adhesive joints where we bond the 2 pieces together. There's flange joints where we leave it up to you in the field to bolt the pieces together. And there's O-ring joints where we slip the 2 pieces together and then O-ring seals the piping. So a button wrap joint, it's the most common system, like I say. It doesn't require any special tooling. It's available for all pressure ratings. It's available for all liner thicknesses and structural thicknesses. Generally speaking, it's going to be about twice the labor of an adhesive joint. It's quite a craft, as you saw the person making the T in the first video. It's pretty much the same process you're going to use to do the button wrap method. So a person takes that resin, they catalyze the resin, they saturate some glass reinforcement that would be in a kit in our example, and then they apply that and roll that out onto the piping with which they've joined together. And this is kind of what the finished joint will look like. And here's some examples of some button wrap joints. And you can see they get to be quite complicated. In the big, large diameter spool on the right hand side, we'd want to have really good measurements there to make sure those flanges are going to bolt together properly. And on the left hand side, you can see quite a complicated little spool that's got a whole variety of shop butt joints in it. But another way of joining the piping is to use an adhesive joint where we bond the 2 pieces together. So in our system, we have a socket and we have a matched taper on both the female and male ends. It does require a specialized tool to cut the taper, and it's really only applicable to certain pressure ratings and diameters and liner thicknesses and structural thicknesses. That's because the geometry has to be maintained to make the joint work. It has the same pressure rating though, the same strength essentially as the butt joint. Okay, so a lot of people are not so clear on that point. They wonder, is an adhesive joint the same? It will have the same pressure rating as a butt joint. And generally speaking, it takes about half the labor of a button wrap style joint. To do an adhesive joint, you cut a male taper on a tapering tool. You put adhesive on both the female and male ends. You bring the 2 pieces together, and we show some clamps here because you actually have to hold it together so it doesn't come apart and you don't draw air into the joint. And then because the joint creates a very thin glue line or thin adhesive line, we actually cure the joint with a heating blanket. And the finished joint is going to be as hard as the original piece of piping. And here are some examples of adhesive joints. You can see the guy's making a flange by flange straight piece of pipe over on the left hand side. Here we're making a flange T for a spool in the middle of the picture. And then over on the right hand side, you can see some long pipe racks, and that's a great spot to use adhesive joints because it's simply slipping the 2 pieces together and holding them in place while you do the joint. And you can have that pre-tapered, that taper that's cut on the tapering machine can actually be pre-done in the factory and sent out pre-tapered. So that's also quite common for rack piping. Flange connections are also very common in FRP. They have the same drilling pattern that you would use in metallic piping. You do have to be careful though, because FRP is not a ductile material. like we were saying about when we were explaining FRP versus metallic. And that means if you have any kind of bending around the flange face, you're going to be in trouble, and you need to use a lap joint style flange for that. So if you look at this valve here, that lining that's in the valve that doesn't come right out past the bolt holes, that's going to be a problem if you use a full face flange. So if you use a full face FRP flange that has the bolt holes in it and you crank down on it, it's going to be unsupported out past that rubber lining and is likely going to crack when you torque down on it. So what you need to do is use a lap joint style flange. And you can see by my thumb there, it's only the FRP hub that's going to press against the lining, and a steel ring slips on behind, and that's where the pressure is put evenly on the FRP. There's not the same kind of bending torque on the FRP, and that's how you need to connect any type of raised face, is to use a lap joint style FRP flange. When it comes to expansion joints, actually a little special there too. You can see here in the picture that the expansion joint has tie rods on the outside to prevent the expansion joint from coming apart from pressure thrust. You can see you'd have pressure thrust at that 45-degree elbow there. So when the pressure thrust comes onto the expansion joint, now all the load is transferred to two tie rods in this case, and you'd have a concentrated load on the FRP flange, which is generally, again, it's not a ductile material. So you'd want to distribute that load by sliding a steel backing ring behind the FRP flange. The load comes on to the tie rods. It pulls that backing ring more evenly onto the backside of the FRP flange. So that's the preferred way to connect to an expansion joint. When it comes to gaskets, really you'd like to use a soft EPDM gasket with FRP flanges. There are low torque gaskets you can get. You can see this one has the sealing rings built into it. You should really contact the FRP manufacturer before you use anything other than a flat EPDM gasket, because sometimes you have to make adjustments in the FRP flange face to match the gasket style you're using. And when it comes to washers, the key really is to just use a narrow series washer. You can see here in this picture, the flange on the right hand side looks like it's scalloped out. It's actually scalloped out because you can imagine the flange thickness needs to come up onto the hub of the flange in order to make the flange stiff enough. And that interferes with your standard ANSI drilling patterns. So in this case, we've actually spot faced it for a narrow series washer. You can see if I used a regular wide washer, it would cut deeply into the fiberglass, which would not be a good thing. And I won't go into O-ring joints. They're usually reserved for cooling water pipe, large diameter pipe, but they certainly work. You can basically install the piping very quickly using a double O-ring system. This particular system doesn't have axial restraints, so you'd need to have concrete thrust blocks where you had major changes in direction, but it definitely does go quickly and works well. Well, I mentioned that you have to be qualified to do FRP piping, and here you can see this is how we do it in our shop. So here's some qualification that went on at one of our shops. The guys would do a qualification spool, and that's what it says in ASME B31.1, B31.3, and an NM2. So if you reference those three codes, any one of those three codes, you're actually saying that all the bonders must be qualified. And to qualify, a bonder has to do a joint, make a qualification spool, and keep doing those joints at least once every 6 months, and then their qualification remains current. So what the bonder does is they make a qualification spool on the type of joint they're going to do, and they pressure test that joint to 3 times rated. The size of the joint they do has to be a quarter of the maximum size they'd like to do in the shop or in the field. So if I do a 12-inch joint in my qualification spool, I'm qualified up to 48 inches. And the other thing is that according to the code, all three of those, NM2, 31.1 or 31.3, the qualification has to be done by a qualified examiner. So it's not practice according to the code, for example, to send a qualified examiner to train one person and then that person trains a bunch of other people. The way the code is written, the qualified examiner needs to train each bonder, and each bonder needs to make their own qualification spool. When it comes to quality control in FRP, most of the laminates you're going to see, it's a visual acceptance criteria that is the overwhelmingly way to maintain quality in the laminate. So there are some ASTM standards. There is the standard in RTP1 or NM2 that lists the qualification criteria for the laminate quality. And here you can see here air bubbles, as you could see when you saw the operator making that T. Air bubbles are your main enemy, and you've got to minimize those. You can see in the liner here we have a maximum of a 1/16 of an inch and a maximum of an 1/8 of an inch air bubble in the structure. And you can only have so many of those. And then there's other defects like pits and blisters and burns and cracks and crazing, and there's a whole list of them here. And some of those are none of them allowed, and others have certain criteria that are allowed. And this is what the QA people are looking for every day when they're inspecting the laminates. There is also an ASTM standard 2583 that explains how a bar call test can be used to check the hardness of the fitting, which kind of gives you an idea of the cure. The resin manufacturers actually tell us what the numbers should be. So for example, 35 is the number we're looking for Duricane 411. So I talked earlier and I said pipe supports for FRP piping are not standard, and that's true. Definitely there are some differences, but there are some basic rules that you need to follow to ensure success. The pipe supports are going to have to made for FRP. They've got to be stiffer than a regular pipe support might be. They're definitely going to be wider than a pipe support. You might generally see in metallic piping. They're going to be lined with rubber to cushion the FRP, and you're going to need more pipe supports than you would need in metallic piping. The pipe supports need to keep the pipe rigid. It can't be flimsy. That would allow local overstressing of the piping. The supports need to be wide enough to prevent pipe loads. Commonly, they're twice the width of a wheel of a steel pipe support. And over time, you can't have steel directly contacting FRP. It'll chafe the FRP and eventually wear through it. And to prevent this, we normally line the FRP pipe supports with an eighth of an inch of rubber. If you want to anchor FRP, you can't just clamp down hard on the support. What you actually do is you make a support and you weld or bolt that support to the structural steel, and then you put a collar on either side of the support. It could be laminated in place or bonded in place. That's what you're seeing in the top picture. There are two collars bonded in place in this case, and that steel support is bolted down to the structure, and that's what anchors everything in place. You can use a flange support to pick up a flanged heavy weight like this valve that's shown in the bottom picture. And you'll notice it's a nice idea to use a flange support because, for example, the T that's coming out on the right-hand side of the photo has a hub, a repad that's going to interfere with a typical trunnion type of support or a pipe clamp. So the flange support is a nice way to pick up equipment. And in generally speaking, I call them FRP pipe supports, but the pipe supports themselves are generally hot dip galvanized steel. They can be epoxy coated, but generally they're hot dip galvanized. The styles of FRP pipe support, the most basic FRP pipe support you're going to see is just a shield. So this shield could be FRP, it could be metallic. It's strapped onto the pipe, and you can see on that I-beam in the picture. Normally in steel, you might just lay the pipe right across the I-beam. That would be a no-no in FRP. You'd want to have at least a shield, which has that rubber liner and is strapped onto the piping. If I needed to guide that piping, remember I said maybe every fourth support needs to be a guide. You could put a U-bolt, but now if I put a U-bolt over the top of the piping, I'm going to need a shield on the top side as well. When you get to larger diameters, you're going to have more of a traditional looking pipe support like this. That'll keep the pipe in shape, and this is also how we could anchor the piping by welding this support to the structural steel and then applying two shear collars to either side of the FRP pipe to hold the pipe in place and prevent it from moving through the support. And on the vertical, it's the same thing. You can't just clamp down on the piping in the vertical if you want to hold it in place. You actually have to put a riser clamp on it and then laminate above the clamp. And finally, that flange support I was mentioning, if you want to pick up equipment, this is probably the easiest way you're going to be able to do it, because you don't have to worry about interference from butt joints and other things like that. So there's your basic styles of FRP pipe supports: your slides, your U-bolts with the shield, your anchor, or that could be sliding as well, or guided, flange support, and a riser supports. However, if you want to get the full array of pipe supports, just go to our website, download our pipe support catalog. You'll see there's a whole array of all kinds of styles of pipe supports. You'll notice there is some trunnions there. We usually try to avoid those, but they are available, and you can certainly contact us if you have any questions about pipe supports. And lastly, I'm just going to quickly touch on pipe stress analysis for FRP piping. It's certainly different than doing the pipe stress analysis for metallic piping. B31.1 or B31.3 are usually what we'd recommend you choose if you're using Caesar or K-pipe. However, at most chemical plants, you're going to use B31.3, and that works fine. We do not recommend using ISO standard 14692. We find that this is a bit unconservative when designing FRP pipe. It's really meant for commodity pipe. And in the near future, you'll be able to analyze the pipe with NM2. At the moment, Caesar and Autopipe do not have the ability for you to pick NM2 as a code to analyze FRP piping. The one thing you're going to need for sure when you do analyze FRP piping are the factors, your inputs that you're going to use in Caesar or Autopipe, your SIFs, K factors, Poisson ratios, modulus values, and of course your allowable stress. They're going to vary by manufacturer. Unfortunately, there's no way around that. The values may be similar from manufacturer to manufacturer, but you really should use the manufacturer's numbers when you go to do your final pipe stress analysis. And we have a document for what we call that HPPE, that high performance pre-engineered pipe, the A150 and P150. We've got a document that tells you all those component numbers that you need to use, and if you had a specialty item of piping that we were making for you, we'd make a variation of that to get you all those SIFs and K factors and allowable stresses. Like I say, sometimes we actually do the pipe stress analysis. More commonly, we're going to give you this kind of a document and tell you how to do it. Maybe take a look at your first few screenshots and say, yep, you're on the right track. And sometimes when you get stuck and you have problems and you can't resolve overstressing problems, you come to us and we'll give you some tips on how you might be able to get around that. One of the big things though, when you analyze FRP pipe is, again, FRP pipe doesn't yield like ductile materials. So you can't use higher allowable loads in displacement cases. You have to analyze all the loads as operating or sustained loads. You can't use expansion cases that you would use in metallic pipe. That's a huge difference. You enter the total wall thickness, and that gives you the correct thermal loads, but then you have to put a corrosion allowance in to assure that the stresses are only calculated on the structural wall. That's the basic fundamentals of doing the FRP analysis. And when it comes to occasional loads, wind or seismic, NM2 actually permits you to use up to 33% more allowable stress, depending on the frequency and duration of the loading. And really, pipe stress analysis is a whole separate seminar we could talk about, so I just wanted to touch quickly on that. Well, that's the end. I hope it hasn't gone over too much. I think we're just around 50 minutes, 55 minutes. I appreciate your time. Like I say, please go to our website. If you have any questions, you see my email below there, but there's more information on the website, more contact information. Please feel free to contact us if you have any questions about what you've seen here, or again, if you'd like to have a live webinar, maybe suited a bit more for your particular application, reach out to us and we'll definitely make it happen. Thanks so much for tuning in. Have a great day.